Android, if you are able to see it. Okay, so it is split into multiple places and it is built separately. So I made it compatible with my device. So if you're able to build any AOSP device, then you can hook into this package. Like if you see the cuttlefish they told in the last talk, every AOSP package you clone will have a cuttlefish in the custom ROM. At least I'm saying, okay. So to build the devices, the custom ROM developers will use few of cuttlefish configs. So like the same way, you can clone a repo called device common car. So that will have all the common car functionalities, and you can inherit with your make flags if you want the feature or not. So this is similar to the approach of custom ROMs. If you're going for a say pixel experience, you would say G apps equal to true, or if you're going for Evolution X, you can build vanilla or without with G apps or without G apps. So it's the same makefile configs, and you can build it for your car. So what this will unlock is if you have a OBD device, you can connect the OBD device to your car, and you can connect that OBD device to your device, and it unlocks way more potential than you think. Okay, so you can control your AC from your tablet and your antennas. And I was able to calculate some very few metrics like the speed, those things, because my own was a basic car, so there was not much functionality in the OBD device. But if your car is advanced car, you can connect the Google Assistant also to move the windows. Those things are very much possible. So that's how it is. Um, that is the basic thing I did. So I'll just go back. There is more to it. Okay, so I used a Android tablet which had nothing. It does not even have a cellular. It's just a tablet because that's how the Fiji gave it. So what I did was I took my another device, MIA2. So it was a small device. So that had every feature, like it had a SIM, it has a SD card, it had everything. So I thought, why not port it? If I'm able to put it in a tablet, I can just put it in this, but with a smaller screen, of course. So I was able to do it. So I was using it in the first place. So before this, there is one more step called as you can use any device, Android device, as a automotive host. Like there is a Android Auto app installed in your devices. You can use it as a host and you can stream it in any device. So that's how the basically the AA car players, Android Auto car players initially worked. So I was trying that, but I wanted native experience. So I came up with that one. So you can check my GitHub. Okay, I will open it. So it will have few things you can use to build it on any device. Like if your device is able to build an AOSP custom ROM, you can just clone this and it will be good to go. So I have some RRO here. You can just inherit the car.make, and I've just taken config from all over the places. That's all basically. So it needs the few services, few configs, and it is just basic flags. So I've inherited from fewer places, and with just this one car.mk, you can just build the automotive for any of your devices which you're building USB custom ROM for. So that will be it, and I'm running out of time. So I will say about my device journey. So I started uh, from a very old Sony Xperia E2 dual device, and I just kept on evolving. And in this device I came, this is a very special device. Of course there were BSP providers here previously, so they would know few devices have very long term support. Like if you are able to see in the recent days, they are providing 7 years of update, 10 years of update. It is not possible without BSP. Okay, you can do it, but it will be a very hard thing. So this device officially launched on 2018 with Android 8 and was stopped in 2020 with Android 10. But currently it is running Android 15. Hope I can able to port it to Android 16. So there are few chips that Qualcomm gives extra support. Okay, so Snapdragon 660 was one such chip, but there was no BSP support at all. BSP usually gets leaked, or someone should expose it, which no one will expose because it is critical to their job. So we will just use the leaks one, or if there are common chipsets like SM8590 is similar to Snapdragon 660, so we will use that leaks BSP to build this with the say AOSP, that is the closest custom ROM to the native CAF. So we will just build it and use the blobs here. So we were doing the retrofitting things to make it work. So successfully it is there till Android. So this chip stopped at Android 14, maxed out at Android 14, so there is no other go. And then we have to, okay, thank you. And then we have to, uh, sorry. Uh, so this chip stopped at Android 14. So from now on, everything we do is pure custom. Even though it was still Android 14, we were still retrofitting many things and backporting because this device is an AB device. But later, Snapdragon had their internal device, and this board has a V2 version where they had VAB support and many new things, so which we were not able to do. So we were doing the dynamic retrofit partition, and we were backporting it and adding some few custom kernel tracing and adding the EROFS partition system, which made uh, this device to revive back to its life. And yeah, so there are some niche Android flags and things in Android custom source where you can use. So there is this concept called Android Go, where Google promoted it very big in Android 10, 11, and in 12 it got reduced. Okay, and after that there was no talk of Android Go, but the config still exists in the AOSP source code. So they have a different boot profile, and they have very fewer minimal startup process from the Android part of side. So we copied those things, we kept it here, because we and also Pixel 3 device is similar to this device in terms of performance, similar. So what Google did was they cut corners, literally cut corners, as in like when you open app, you will not have the bubble animation, you will have the square animation, and it will scale to the screen size. So those were some vendor configs which were able to we were able to copy from the Google Pixel 3, and we were able to port it here. So by doing these kind of things and updating the kernel, and this device was launched in 4.4, and there was few initial works of 4.14 because the chip supported up to 4.19, but no one dared to do it. So, but a few people, thanks to them, did it. And then later on, I took the 4.14 and started working on Android 4.19 kernel, and that was able to boost it because Android locks you out of a kernel. Like a few versions only support few Android versions. If you wanted to use more, you have to add extra code, which most custom ROM people are not willing to do. It is a real hard pain to get your code there. So to go with the flow, you have to keep updating your kernel or adding backports. So I just update the kernel, and with some CPU scheduling and storage optimizations, I was able to do it. I basically disabled almost all the services on the phone. Of course, Lineage does disable most of the things, but even after that, you can disable your device side, vendor side of the things. So by doing that, you can optimize a good performance. And also there are some efficiency flag, as I said, like you can change the hardware renderer UI, you can change what should be the composing scale, those kind of things when building the Android framework itself. So the Android UI framework application itself will work in optimized way. So I added few of those things, and I was able to make it much better and faster. And yeah, if you're doing any kind of things like this, post it on public forums, open source. I did not market it big because I just did it for 2 years and then the device died. So I did not have any other device to keep testing on, so I did not move forward. But it is still open source, you can still get it and call the car.mk and use it out of the box natively. And you can add GAB support, but the current one I did not add because DMCA strike down. But if you have a separate one, you can separately flash or GABs also, that will also work for you guys. And yeah, that's all. You can, if anyone wants the repo, this is the repo. It's in my GitHub. I am Immanuel Raj slash device common car. And this is what, if you want the configs of the device which I used. So this is my work in Pixel experience. Sad life, they are no more today, but they did a great job. So I added few flags here. So this is how a basic Android makefile would be. So you can check this out. This was done for a, so this is currently in Android 14 branch, so they killed it in Android 14. So you can check my profile, you can see here. So that will have Android 15 configs for the same device, including kernel, everything. So with that being said, thank you. Anyone has any doubts or questions? Thank you.
Thank you very much, Immanuel. Our next speaker is Jaimin, who will be talking about Libcamera and AOSP. Yeah.
Yeah, hi all. Myself, Jaimin Parmar. I am working as a senior software engineer at Tech Mahindra. So basically, today we are looking into one of the open source Libcamera stack and how it will be potentially the next camera HAL for the AOSP. What today we are going to cover is this uh, open source sleep camera, their full stack, and how it can be integrated into the Android, and some debugging hooks if you are planning to bring up this sleep camera into your custom SoC. Okay. So when we talk about the camera, basically, so when just we think about the camera, what comes into the mind? So basically, has the, let's see, many of you has developed the V4L2 camera app. So basically, V4L2 camera app directly talks with the kernel drivers, and basically that will leverage the hardware capabilities, and you will get your images. So if we talk about the for L2 camera app flow, so this is a very simple and generic flow before L2 camera app will follow. So first thing is it will query the capabilities. So based on the capabilities, it will set formats, and after setting the formats using the for L2 ioctl calls, it will request for the buffers. It may be the DMA buffers, or it might be software buffers, and then you have to the queue the buffers, and after queuing the buffers, you can start the stream, and the cycle of the queuing and dequeuing goes on unto the stop stream. Okay. So basically, when you have the simple camera hardware, everything goes right. But let's see, the things change now. So how this modern camera basically looks like. Basically, so whatever the parts you are seeing in slides, basically in the right of the dotted red lines, it is basically inside one SoC. Okay. So basically, whatever you are seeing, the black correction, defective pixels, I2C controller, CSI5. So it is inside one of the SoC, and these are the hardware blocks. And if you seeing, okay, the left side of the dotted lines is the camera sensor, external camera sensors. So let's just, okay, move through the how this modern camera basically, okay, works and looks like. So camera sensor basically has a control unit over the I2C bus, and you can send okay, instructions to the camera sensors, and whenever the data comes, so data basically comes over the CSI2 pipeline, and it has a CSI5 basically that will handle, and based on the bus, it will go to the your black level. So these are the basically the ISP blocks, image signal processor blocks. Okay. So this is the very generic and typical flow. So basically, means if you took the real hardware, it goes complex, but this is just to understand, okay, how the camera pipeline works. How took this. So basically, once your maybe the raw image or the bare sensor image comes, it will go to the black correction. So basically, sensors have the dark current. So basically, if you have the black pixel also, then it will draw some currents. So okay, to minimize that, and basically it has some offset, okay, to means get the correct pixel value. We have the black level correction, Then it comes to the defective pixel correction ISP blocks. So basically what defective pixel correction ISP blocks is do is at the time of the manufacturing some of the pixels are defective. To correct that defective pixels, we have the defective pixel correction, and basically what are the defective pixel correction are stored under the some of the non volatile memory, okay, where from you can take okay, what are the non pixel defective pixels, and you can correct it. Then it will go to the demosaic where you can convert to the RGB, and it will go to the color correction where you can naturalize and adding the more colors, and after that it will go to the scaling where the downscaling will happen. So basically these are the okay, how the modern camera basically looks like, right. So let's see if we want to okay go one slide back and wants to control this from the camera app, right. So it will be very difficult to, because these are the different ISP blocks and you have to connect the each blocks. So basically if you see CSI5 black correction lever, so to control from the kernel layer we have the media controller, we have the V4L2 and media controller APIs. So every block has the seeds, every block we will call it entities, and every block has a source and a sync pad. So basically if we see the camera sensor, right, so it has a source pad only. So we will call it the source pad, means it is giving you the output only, and it is coming with the CSI. So here we will call it the sync pad, and again it is sourcing like this comes, right. So basically here when you okay come to a modern camera, you have to make the pipeline to get the correct result. Okay, so basically let's see if everything comes to the application layer, right. Application developers has to more aware about how your hardware looks like, and it will be difficult. So this is a OMAP 3 camera in Nokia, and you can see how complex the camera pipeline will looks like. Okay, okay. To ease the basically this means to don't have the camera app developer don't have to more aware about the how the hardware underlying hardware works. Here comes the Libcamera. So what is the Libcamera? So Libcamera is a complex camera support library, and it is basically supports the Linux, Android, and Chrome OS. Sorry. And the Libcamera, what is and why we have the Libcamera? So first thing is Libcamera is the open source, and it is driven by the Linux media community, and it has and why? So basically it is a full user space stack. Okay. So basically it does not contain anything related to the kernel. So here we are not talking anything about the kernel, and if you want to okay make your SoC compatible with the Libcamera, you must have the media controller drivers upstream. So that will leverage the capability of the media controller APIs, and Libcamera will talk with it. And so basically when it comes to the camera HAL in the AOSP, so most of the OEMs don't give their camera basically source code. They are all the proprietaries, right? Because they are, there is the image processing algorithm implemented. So Libcamera also gives okay vendor specific closed source IPA implementation integration. So we'll look into the more details in the architecture, and it has a reference implementation for the Raspberry Pi also, and Intel IPU3 and Rock chips, and basically it will give us Android OS wrapper HAL. So you can directly integrate it with the Android once your pipeline is up. So Libcamera is nothing but one towards the adaptable layer for the camera integration. Okay, so this is the how camera stack looks like. This is a Libcamera stack. So on the top we have this adaptation layer. Here the adaptation layer, and we have the application layer. So basically application will talk with the adaptation layer, or application will directly also call the Libcamera also APIs, right? And if you talk about the Android camera framework, so basically the in the Android camera framework at the top we have the applications, and then it will okay, go to the camera HAL, and basically this HAL will load the Libcamera, has the Libcamera has a plugin, and Libcamera will take care of the all the your hardware specific kernel drivers. So let's a little bit okay, deep dive in the Libcamera architecture. So in the Libcamera, whatever these blocks you see here, so in the yellow are the device agnostic blocks. Okay, whatever the means, it doesn't depends on the your underlying the hardware. And here you see the this a pipeline handle, right? The block in the green, basically this green. So this is a device dependent. So all your device based logics will be come here, and this IPA module, image processing algorithm, uh, basically this will be closed source also, or the open source also, is based on the your implementation. So basically what comes in the pipeline handler. So basically what will a pipeline handler do? Let's see, if you have the complex ISP what I have shown earlier, and basically pipeline handler will okay, uh, if you have more than ISP, then pipeline handler has implementation of the what are the different types of the ISP you are going to support. So basically there will be the match function, so that will match okay, what are the ISPs your pipeline will handle. So basically in the one Libcamera you have the more than one pipeline handler also to handle the this ISPs, and it will this pipeline handler basically take cares of the your stream configurations also. Basically you have the stream configuration like the still camera, viewfinder, video recording, and and you can also the policy also, like what are the best ISP, okay, ISP output from which I can get the best video. So based on that you can do the configuration also, and based on the hardware in the pipeline handler, based on the hardware, let's see, this Libcamera will support the multiple stream also. So there you can configure how many max stream this my hardware will handle. That also you can configure also, and the logic for the loading the this IPA module means what are the what type of the IPA modules you want to load basically. Okay. Maybe IPA module you can load has a one has a shared library also there, or it may be directly compiled with the Libcamera also, has a static library. And if you don't want, and you just want to your IPA module has a like closed source, so basically it will what this Libcamera architecture will do, this your IPA module won't run in the Libcamera process. It will fork the process, and it will run in the sandbox, and the this communication between the this IPA module and the Libcamera is on the Mojo IPC, basically they are taken from the Chromium. And if we take a look at the core libraries, okay, to okay, implement the pipeline handler and the IPA module, so they have some core library where the camera configurations and the camera based like what is the capabilities of your camera, and let's see if you have the IMX219, then what is the physical size of your camera. So that are all given as the camera sensor info, and after that there is the kernel and hardware. Okay. So basically this is the how the structure of the Libcamera looks like, source structure of the Libcamera. It has a this is the build directory. So basically it will generate once you have the run the build commands. It doesn't come with the git tree. So there is a documentation. You can find the documentation guide, include headers, and full implementation of the source you can find inside the source code. I'm not going to okay get more deeper into it. And here in the Android, we have the AOSP HAL wrapper, okay, just to get compatible with the AOSP HAL. And in the IPA, we have the means algorithms, and they have already implemented for the IPv3 Raspberry Pi, VMC. It is a virtual, and Libcamera source, and they have the also language bindings. Okay, so you can develop your Python application on the top of the Libcamera. Okay. So basically, what it takes to integrate it with the Android architecture. Okay. So basically, this is the how the Android stack look like. So I'm not going to much deeper into it, but this is a let's see if you want to talk has a camera app. So there is a camera app. Then there is a framework APIs basically that API framework APIs, and we have the hardware abstraction layer. So basically, this is the where our Libcamera comes into the action at the HAL layer. So basically, this all are this camera app and the Java APIs are not going to change when we are integrating the Libcamera. Okay. So let's see. We will go through flow of the how the camera will work in the Android AOSP. Basically, I'm not going to cover here the camera app. So we will directly come with the camera service. So in the AOSP, the camera server basically it is started by the init process only. So here you can see this is a service camera server, system bin camera server. So this will be started at the boot time only by the init process, and this is how is the init RC file will looks like, and it will register. It has the AIDL interface. So basically, the camera app and the underlying HAL will talk with this camera server using the AIDL. So once the init process will start the camera service, there it also start the camera provider manager. So what basically this camera provider manager will do is the camera provider manager responsible for finding how many camera HAL. So basically, camera provider HAL is what will provide the camera device to your Android upper layer. So camera provider manager will launch and it will it will ask the system, okay, means how many camera provider managers we have, and it will register with the camera server. Okay, now we will go to the camera provider. So basically, this is the big picture of the this camera provider. So this is the AIDL implementation of the camera provider. So I just want to show the libraries only. So in the camera provider, basically you have the one camera service, which will be started by the init.rc init process only. And basically, if you let's see, if you don't have the Libcamera, so full is implementation will be done in the .implementation.so file. So at the runtime only it will load .so file, and here whatever you can see in the last block, right, the camera.libcamera.so, libcamera.so, and libcamera base.so. So this is the where the Libcamera comes into action. So this camera provider basically calls the get hardware module, and it will load the this camera.libcamera.so files. This is where the Libcamera init process and the main architecture comes into the action. Okay, so now we will take a look into the Libcamera initialization flow. Okay, so basically, once let's see your library is loaded by your Android HAL. So basically, Libcamera is like a plug and play like a module. So you can directly, if you have the camera provider HAL, you can directly call that SO library, and basically it will do the DL open, and you have to call the camera init. And this all the functionality of the camera init is in the source Android camera HAL manager.cpp. So this is the file from Libcamera git tree. So let's take a look. So basically in the this Android Camera HAL 3 wrapper of the Libcamera. Okay, so this will HAL module InfoSys. So it will you can see camera module APIs hardware, and if you come here you can see the HAL init. So basically this is the init function. This init function was called by your camera provider HAL only, and initialization will take place. So this is the HAL init process, and it eventually initialize the camera HAL manager, and it will call the HAL instance init. And this is the how the after once you call the init, so it will start the camera manager. So this is the camera manager from the Libcamera, and once you call, then this a device enumeration will happen. So what it will do is the Libcamera itself will go to the if you have the UDEV based device, so it will go to the UDEV's rows, and it will try to find out what are the media devices you have. And if you don't have the UDEV, it will also go to the sysfs media, and it will try to find out all the media devices. Once it has all the media devices, then basically it will try to get its entities and capabilities of the ISPs. Once it will get the capability of the ISP's name of the entities, it will call basically this create handlers. So basically what this create handlers will do is create handlers will get all the available pipeline handlers available in your Libcamera, and one by one in the pipeline handlers you must have the one match function. So it will match ISP entity's name with your pipeline handler. If it's match with your pipeline handler, means your pipeline handler will able to handle the ISP, and eventually it will call the add camera, and add camera basically emits the signal. So it emits the signal, and it will go to the upper layer where we have initialized our camera HAL 3 wrapper. Okay, once this camera add emit signals goes, then it will call the camera add, and for the AOSP they have the configurations file. So in the configurations file you can configure what are the means camera nodes you want to show into the upper layer, and basically the initialization process will take place, and it will also initialize all the capabilities of the camera. So if you take example of the camera 2 APIs in the Android, so it has so many capabilities. So let's see if your Libcamera architecture something missing one capabilities, then it will fail, and it does not initialize that camera node because it does not have the proper capabilities, right? And if everything goes right, then it will send one callback signal to the camera framework that one new camera node is added. Okay, so if everything goes right, then you can if you have enabled the debug logs, then you can see the camera ID added successfully. Okay, so basically this is the sum of means in the I've just discussed, right? So you have the camera HAL.yml file, so it will be read at the initialization only. So to get your camera position, like the front or back, or how much rotation you want. So basically, let's see, if you don't have this file, then your Libcamera will be initialized, but it doesn't show in the Android, because this is a very specific file to the Android, and you have to add all the properties. Okay, and you have to also define the location of the Libcamera, means Libcamera HAL. So this is just course implement, and this is the slides we'll go through, and this is the camera capabilities where all the capabilities initialization will happen. So if anything is missing, you can add there. And this is just a build system, so it is using the Mason build system, and backend has the Ninja. This is the some of the commands, basically Mason setup build, okay, configure build, and you can also you have the choice to, okay, what are the pipelines you want to build and what are the applications you want to enable in the Libcamera. This is the build configuration. Basically comes once you run the build command, and it will tell you, okay, what are the options you have enabled. Okay, but here the what has the Android developer, the missing piece is the Android BP or the Android MK. So it is the Mason based build system, so it does not have the Android BP or the Android MK. So in the community, from the long it is going, that means how to integrate this into the tree. Basically, because we cannot write the Android BP directly or Android MK, because it is some for the IS IPC communication for the Mojo, Libcamera will generate intermediate files at the build time. So that you have to hardcode into the Android BP, and basically this is what suggested by the this main architect Lauren Pichart. So this is the suggestion, okay, given by him. And okay, I just want to discuss some of the, let's see, if you want to bring up your SOC Libcamera in your SOC. So first thing is how to enable the locks, right? So basically, really, I spent 2 to 3 days just to enable the locks on the Android. So because if you saw in the documentation everywhere given, it is like you have means this is the environment. So if you run into the Linux command line, you can directly set the environment, and after you run the library, okay, it will take from the environment. But in the our Android, it is not the okay case. So basically, in the whatever your RC file of your camera HAL camera provider HAL, there you have to mention what is the log level and what is the log file. And let's see, if you don't want to do this, basically what I have done is I have just hard coded the in the log file only. So to get rid of the every time means changing the provider. And before coming to the very upper layer, if you want to let's see, if you are the pipeline handler, everything, if you want to just check how much camera Libcamera will work or not. So basically there is a cam tool already present in the Libcamera. You can build it, and if you run the cam -l, means it will list the what are the available cameras, and you can check your pipeline by cam -c1. So means it will capture from the camera 1 basically 10 frames, and it will dump to the file location. And after the dumping, if you want to check the camera, you can use the Fmpeg or some other tool, okay, to get the look into the pictures, means how your camera looks. Yeah, and from the Android point of view, I am using the DumpSys media camera. So this is just a code snippet. So let's see if the Libcamera underlying works, but something goes wrong on the camera HAL. And it is not able to means add the camera at the HAL upper layer, means framework layer. So if you do the DumpSys, you can see here there is no camera. So it will show the what are the camera devices for the clients. So DumpSys is a very useful tool for the debugging. And in the DumpSys, you can see also basically what are the camera providers HALs which are registered with your camera server. Okay, so basically this is the code snippet for the failed scenario. And this is the code snippet I have dumped for the success case. So here you can see that I have one camera. I have the camera device, and if you see here, so basically we have the true providers. The external provider, and this is what my one Libcamera, and it has also one devices. So in the DumpSys also you can see the what are the active clients you have. If something goes wrong at the application layer or framework layer, you can see in the DumpSys logs basically. Okay, so basically these are the references what I have used, and yeah, thanks.
can Libcamera also be used in Linux
Yeah, of
Android
course.
devices like post-market OS?
Yes, of course. Of course. But basically, the Libcamera is like you must have the hardware support. Okay, you have to add the hardware support there.
Can this Libcamera also work on Qualcomm-based platforms? Because I know that Qualcomm has their separate camera stack.
Yeah, so basically the Libcamera is basically what if you just okay consider these slides. So basically it will take the capability of the ISPs, means IFC. So if you know the underlying hardware, okay, ISP hardware of the Qualcomm camera, Qualcomm stack, and if you can add the support for that, then it will of course work. But yeah, for that you have to add the support.
It will be difficult as I believe that everything runs in library format in Qualcomm stack for ISPs.
Yeah, that's why we have the Libcamera, right? That's why we are going to miss it, try to add the support for the Mali C55 like that. Yeah.
I think one of the post-market OS devices. I think I think one of the post-market OS devices could be Pixel 3a or uh, yes, OnePlus 6T or something. So they have the camera working, and I think they use lip camera. I may be wrong, but I think I just seen it last week or so. So because they are very excited to have the camera working. It's very difficult to get a camera working, especially on a production device where you have where you don't know what CSI or CAMCC. CAMCC is the Qualcomm driver, whatever magic they are doing behind the scenes.
I think good talk for outside in hall.
Sure, definitely. Thank you
Okay,
very much,
thank you.
Jaimin. Our next speaker is Mr. Khasim. He'll be giving a different take on AOSP. It'll be interesting to hear.
Okay. Hello everyone. Good afternoon. I think we are almost like near lunchtime, so I'll try to cover very few slides so that it keeps you engaged. And the topic that I have taken is mainly to show how we can take some kind of a fresh look on Android ASP's role in embedded systems. So the area that I want to take is like taking Android beyond mobile, beyond uh, TVs and automotive, right? I work at Texas Instruments, and I have been using Android AOSP project for quite a few years now. Starting, I heard Android 12 and 13, but when I started on Android, it was like Android B, like butterscotch and cupcake and donut. So I started using Android back in 2008 9 time frame. So have been involved in Android projects for a long time now. And my area of interest always has been to use Android for non-mobile, like wherever Android and Google generally prefers using Android for their own concepts, and like especially mobile and TVs and automotive. I have always tried to use Android for non Google's projects. So, and I have been very successful in that, because Android is the one good part of Android is it's completely open source projects, and AOSP has definitely been very useful for this prototyping of Android for non-mobile applications. So just to give an historical overview, like as I am showing on my slide as well. So, have been using Android since 2008, and built like as part of TI, and as well I have seen many customers using Android for non-mobile application spaces wherever there is an UI entity, right? If you want to have some very good jazzy UI, and I have seen customers building products using AOSP project, be it medical applications, like where you have UI for medical applications, industrial HMI, big kiosk, and today we are seeing like kiosk used in EV charging stations and many such places, right? There are many end applications like consumer appliances and things like that. Wherever you see a UI based device, Android is the first best fit that goes there. And also connected applications, wherever you have some devices which needs to connect to internet of things, or in any internet application. So Android has seen, AOSP projects generally has seen benefits there. So the key advantages in these areas, mainly it is very portable, UI advantage, and Linux based software stack. So anything that you need to customize or optimize, you can do in Linux, and that gets carried over into Android distribution, right? So or Android application layers. So these things have definitely made Android AOSP project a scale into non-mobile and non-AOSP, and sorry, non-mobile and to non-TVs and non-automotive segments. And this is historical thing, right? So today I just want to show one quick video here. Before we video, I just want to show. So this is a screen. I'll tell you what exactly this screen is about. But this have a video of an embedded system where this screen is being shown. Like you can just see like the kind of skins that it is showing, the movement of multi-touch connectivity, connecting to sensor, different types of sensors, connecting to cloud, or connecting to network applications, right? And this is one. And I also have a video. Let me see if I can. Yeah. So this is an analytics. So you can see like it plays. So there is an audio classification model running, and that basically says now this is a police car siren here, right? So I just showed you historically what has been done in Android, and I just shared with you an embedded system of current day. And the device that I showed in my video there is an embedded system which is running ARM Cortex A53 dual core, no GPU, no AI accelerators or no NPU inside, and no audio acceleration, nothing. It is a bare metal dual core Cortex A53. So it is TI's latest generation AM6, like AM62 series of device, AM62L we call. Okay, so it is a very light version of a microprocessor just running bare metal Linux. So embedded systems has evolved to a place where a simple microprocessor, or I mean to say Linux has evolved to a place with all its other distributions. The skin that I showed is an LVGL graphics stack which is giving you the UI screen, and there is an audio analytics which is running on just Yocto based distribution, which is giving audio classification and audio models which can easily classify what type of audio is getting played and things like that. So um, the current generation of Linux plus Linux distros, be it Yocto or Debian or Buildroot or any such distros, are giving the flexibility that an end equipment needs for any kind building any kind of UI or bare minimum analytics, or analytics over the edge, or edge AI, whatever you call, right? So so today embedded systems are able to get the power of Linux and Linux distributions and scale to the needs of end consumer without using Android, right? So earlier, in order to get to that level of UI and analytics, we were supposed to go to Android, and Android phones and Android tablets were giving you that kind of UI richness. But today, even with just bare metal build root kind of an distribution, you can get to that level of UI experience. So then, is it an advantage to even consider going AOSP route to build that kind of richness for embedded systems or embedded equipments which are non-mobile or non-TV or non-auto? Definitely, there is lot more room and advantages that one could get by going to AOSP. I already showed in my previous video where embedded systems with Linux and distros are already scaling to the richness of Android UI, but still by using AOSP for embedded equipments, you can definitely get a lot more, right? Android is also evolving on other side, but the only caveat there is Android needs GPU, Android needs high-end accelerators, Android needs multi-core processors for doing its processing, but that is on the hardware side of it. But the kind of flexibility it offers for an end equipment is still vast and wide, right? So some of the key factors that I have listed here, even for user interface, right? Full featured UI toolkit that is available on Android, you won't get in any kind of Linux distributions that we have in the market today. The kind of device ecosystem that we have, or the app development ecosystem that we have for Android, you won't find it very easily when you migrate to embedded space, like be it Qt or be it an LVGL, or the developers that we have today in the industry today are very limited for these kind of UI toolkits. And the kind of time to market that you can build by going to AOSP and Android is very fast, very quick, right? Like you pick any off the shelf tab or after off the shelf mobile, you can start quickly prototyping your end use case or end application. Same thing to do with for an embedded equipment becomes too complex, and these are some of the areas where Android AOSP still stands out for building any kind of an embedded equipment with AOSP project. So, what are the end equipments and opportunities that we are talking here for using or leveraging AOSP? Like as I said, majority of your mobiles are Android today, and then TVs for smart TVs and automotive infotainment, and these things are Android today. Apart from that, when it comes to very core real-time operating system requirement or real-time needs, like if you see the graph that I am showing, if your embedded equipment needs a very hard real-time processing, that is not the area where you would want to use Android, right? And if your UI needs are very minimal, that is not the area where you would prefer Android usage, right? So the green color area that I have shown here, where your UI richness is high, your connectivity requirements are high, and your real-time determinism is low, in such segments you can definitely start using AOSP projects. So some of the key examples are like consumer appliances, medical end equipments with UI, and industrial HMI and infotainment systems. So all these segments will cater to this AOSP usage. So then what in AOSP, like is AOSP best suitable or direct fit for building embedded end equipment? Like if you see in those lines, I would say there needs to be more simplified versions of AOSP to fit into an embedded equipment, right? Today, when I talk to my customers who are building their end equipments, they even find Linux subsystems very hard, right? Like they think Yocto is very difficult for them to understand. Building Debian distribution based end equipments are very difficult for them to understand. They are coming from microcontroller to Linux, or Linux to a distro based Linux and things like this. So for them, all these things are way too complicated, who are so used to real time environment. So for them, we have to make Android AOSP very, very easy, very thin and lean, very good recipes to build, like PLCs or your embedded HMI, or you are building a simple UI based solution. So there should be ready made populated what do you say, stacks, which because these end equipment manufacturers can use and go into production. So it should be completely hand cooked devices. Like if we can build that kind of distros, it will definitely enable usage of AOSP into non-mobile applications. So there are tons of infrastructure projects, open source stacks and tools and everything which is available in AOSP, which will definitely benefit a lot of end equipments, right? And AIML is one part, development tools, then the complete CVE management and long-term maintenance, OTFA, all these things are way too what do you say, way too important concepts that can be leveraged from AOSP for building end equipments on embedded systems. So this is what I had to say here, and before I end my session, I just want to announce this new Beagle Y AI platform, which is on TI's AM67 processor, which has GPU and which has AI accelerators, and it has multi-core A53 ARM core running. And if you are interested in building any kind of end equipment solutions on these platforms, so and if you want to join us in building Android for AOSP projects and making AOSP projects better for embedded systems, then feel free to reach out to me. We are definitely willing to collaborate with you in an open source way. Reach out to me and I can definitely ship you a Beagle Y AI hardware platform to do this Android open source software development. So I'll stop here, and feel free to reach out to me later after this session, and we can definitely discuss on how to enable embedded systems with AOSP. Thank you.
Do we have any questions? Thank you very much, Khasim sir. Sorry, I'm struggling with the resolution change on my device. It's already present. It's not. I know it's somewhere, right? No mirroring, so I need the speaker notes. So that's fine. That's fine. Okay. This one. Now. View. Now I will drag this one. It's not going right. It's not going. The dragging is not working.
Now just move it
Okay.
and see.
Which one? Where?
Try to move it.
Where?
This side, right, left. Dekho.
Oh, this is fine now. Okay. Um, Hi, sorry about the hiccups here. Welcome to the last session of AOSP Devroom. My name is Amit Pundir. In this lightning talk, I'll share my experience of booting AOSP with upstream Linux kernel and making that upstream build somewhat usable by using open source stacks or open source HALs. But before we begin, here's a quick disclaimer on the trademarks and copyrights. About me, my name is Amit Pundir. I'm a senior engineer at Linaro. I've been doing AOSP bring up and BSP integration for last 15 years. You can find me on these IRC channels. So in this session, we will look Android under the hood and explore whether it is possible to boot upstream Linux without any out-of-tree patches. Boot AOSP on upstream Linux, which is not carrying any Android-specific patches. That is no Android common kernel patch set. Well, spoiler alert, it is possible, but we will soon find out at what cost, right? Then we will take a look into the bare minimum useful Android common kernel patch set that I still carry on my tree, and I'll provide the reasoning behind that. Finally, booting Android up to shell prompt or ADB shell is not much fun, right? Android is an interactive OS. It is a user-oriented OS. So I will extend on that topic, and I'll talk about how to make that upstream Linux kernel build more usable by using upstream open source HALs like Mesa, ALSA, and other open source bits to make sure that we get the basic functionalities like the display, audio, Wi-Fi, and Bluetooth working on that device. So a quick slide on why we are doing this and why do we care. So why do I as an upstream developer care about this? And why do you as an end user or as a device manufacturer should care about it? So we at Linaro maintain AOSP on a variety of member devices. We make sure that the upstream projects that we use in our AOSP builds that we care about, for example, Linux kernel, Mesa, DRM hardware composer stack, etc., they don't break AOSP on every version release, or we do at times test the upstream versions as well. And vice versa. We make sure that whatever changes are landing in AOSP are compatible with these upstream projects. The list of these external projects, they vary depending on the level of functionalities which you provide or the device which you are testing on. Now, why do you care, right? So the first thing is, the most important thing is the device longevity. The more you stick to the upstream stack, the more your device is supposed to get the upstream features or the security fixes. You are not locked into the vendor BSP, right? closer alignment with upstream track. It gives you faster access to new features and security fixes. And more importantly, there is no vendor lock-in, which result in faster uptake of software upgrades. Now, booting AOSP with upstream Linux kernel, right? It took us a lot of time to reach up to this point, but yes, it is possible. The basic assumption here is that the upstream kernel I'm talking about has the device support which you are trying it on. All the patches which are required to boot AOSP from the Linux kernel point of view are upstreamed. All the patches, I mean all the critical patches, right? The last critical patch related to the anonymous shared memory tagging, it landed upstream in somewhere in between 5.12 and 5.15. So hooray, let's get started with that. Let's prepare Android dev config, do a build, create our Android boot image and boot up. But will it boot though? Well, most likely not, because your user space is most likely not ready for that. So all this time I was talking about upstream kernel, can it boot on your device? Can you boot AOSP with that? But you do need some AOSP specific, the user space specific changes as well, right? AOSP still defaults to the HMEM driver. HMEM driver is used for shared memory usage in between the apps, in between the core framework. And SE/Linux by default is in enforcing mode too. And when you switch to an upstream kernel, you will realize that because there is no HMEM, it won't boot. And there is an alternative to that. It's called memfd. It's again an upstream driver. So all you have to do is you have to provide an user space hook, enable memfd, and then you will see that, okay, now it is still not booting because the memfd support in AOSP is still a work in progress and it fails somewhere while talking to SE/Linux, because SE/Linux policies are in enforcing mode and the kind of access memfd need is still not upstream. By upstream, I mean it is still not in AOSP. So again, I've talked about the dependency of, it was part of the next slide, but in the flow I just kept talking about that. So in this slide, we'll talk about Android common kernel versions and we'll talk about the HMEM, SE/Linux dependencies, which I sort of already talked about. But so Android common kernel version, think of it like a Linux fork, which is maintained by a distributor called Google. It is similar to how Ubuntu maintains its Linux fork and other Linux distributions maintain their Linux kernel fork. Right? It is a base for all Android devices. This is what Google shipped to the BSP providers, the vendors, and vendors provide it to ODMs, and finally it lands in your end user device. Now coming back to the AOSP dependency on out of tree patches, which is HMEM and SE/Linux. As I mentioned, AOSP has a boot dependency on HMEM driver and currently it is being replaced by memfd, but the transition is still a work in progress, and to work around that, you have to make sure that SE/Linux is in permissive mode. Another useful feature which I have listed down here, and it is still not upstream in Linux kernel, is the metadata partition encryption. If your device, or if you want to try it out, right, booting AOSP with upstream Linux kernel, you have to disable the metadata encryption. I've shared a user space hack of mine for reference. This is a user space patch which I use on my device. You will get a fair bit of idea of what you need to disable or enable to get the upstream Linux and AOSP working. As per me, I do keep HMEM and metadata encryption Android patches in my tree because that's a lot easier to maintain. I don't need to go back and forth, change my user space while I play with Android common kernel versions as well as upstream Linux kernel version. Unless I absolutely have to, because when you report an upstream Linux kernel breakage, there are few maintainers which do not like having an out of tree patch. So they insist that if you can reproduce it on upstream Linux kernel version, then only we will take it as a regular regression, otherwise we won't. Right, so you can have a detailed look at the Android common kernel patches. This is where the patches are hosted. It's on android.googlesource.com. Last time I checked, there were about 180 plus patches, which mostly include the GKI defconfig changes, your vendor hooks, a few binder patches, ashmem, and DMA buff and DMA heap patches as well. Right, so now that you have upstream Linux kernel booting on your device, we'll talk about how to enable graphics on that. Right, I'll be falling back to Mesa for that. Handful of Mesa drivers support GLES and Vulkan implementations, and they have inbuilt AOSP support as well. So, and so does the mini GBM allocator and DRM hardware composer too. So it is just a matter of enabling the device or platform support for your choice. I have listed down the configuration which you need for. So this is generic enough, but if you look into if you take a closer look, you will see that references of FreeDreno and Vulkan, which is mostly the Qualcomm side of graphics. But these are highly customizable, and you can just use whatever Mesa graphics driver you are using. I've highlighted that pre-built Mesa part explicitly here because Mesa build support was unfortunately broken in AOSP because of some cross-platform graphics stream changes when I checked it last time. So these instructions are here just to do the installation part. So I'm not actually building Mesa as part of my AOSP. You can do that. I have a patch set for that. We do support it as part of our devices. But as I mentioned, it is broken right now. So I don't recommend that unless you want to fix it, right? Because why not fix it upstream, or why not send the patches to AOSP? And in case you don't have a GPU available, right? You cannot use Mesa. You can always fall back to the software rendering part. AOSP has an inbuilt stack which provides the software rendering part, software rendering support. They spell it as Swangle, SWANGL. It's a combination of Swift Shader project and Angle project. I hope it is called Swangle because that's what I've been calling it for the last 3 years. To enable software rendering, you just have to enable all these configurations, and that's all about it. In case you don't even have a working display, what do you do about that? In that case, you can fall back to using a virtual KMS driver, right? It's a inbuilt KMS driver. It is part of your upstream kernel. You don't get an actual display, but the display is there, right? In the background, somewhere in the buffer it is displaying. You can use screen capture, screen record things to capture the display. I would assume that you will use something like this if you're running a headless system, right? And once we have the graphics sorted out with the upstream Linux kernel, we can start looking at enabling the audio and the Wi-Fi Bluetooth part. Again, the good news is that AOSP's generic HAL supports ALSA interface, and ALSA is the most common audio interface with pretty much all upstream driver supports. So again, it is just a matter of enabling audio HAL and maybe debug utilities like TinyPlay, TinyAlsa. These are equivalent of running ALSA mixer and ALSA play commands, which you are used to on your Linux device for debugging purposes. And for Wi-Fi and Bluetooth, again, we don't have to look beyond the AOSP stack. The existing HALs in AOSP, these are again the external projects, but they are part of AOSP, like WPA supplicant, which you can use to enable Wi-Fi on your device. And for Bluetooth, if your platform, if your upstream drivers support the SerDev interface, that serial device interface, for some reason they call it SERDEV, and I keep calling it SerDev. Again, I don't know if it is, if I'm doing it wrong, but this is what I've been doing for the last 3-4 years now. So yes, with SerDev, with WPA supplicant, if your driver supports it, you can get the Wi-Fi and Bluetooth working as well. And that's about it. In this session, we have learned this small lightning talk. We have learned that we can boot upstream Linux kernel on your upstream capable device, and why not just stop at the prompt, you can have the display working as well, along with the Wi-Fi and Bluetooth and audio, as long as your device, your upstream driver is capable of that, because AOSP can handle it sufficiently well. I won't say it is comparable to a vendor BSP with a lot more optimizations and a lot more tricks which goes behind the scenes in the Android common kernel or in the vendor BSP, but you'll get a working system. And if you can port a few things from post-market OS, for example, the modem manager, right? Because I have tried this whole stack on what was the phone name? Poco F1, right? I can get all these functionalities working on Poco F1 with upstream Linux kernel, right? The only blocker was the modem manager, which was not working. Now it works on post-market OS. We need someone to just do that on AOSP. We tried it. At some point, we could connect to the radio station. We can get the signals and other basic codes, but we could not get the calls or the data working. The problem with modem manager is it is based on dbus, and so when you talk about modem manager, you talk about dbus, you cannot port the complete stack. People have done it. I've seen that. Glowdroid has done the complete stack, but I think it's an overhead. So sorry, I'm running out of time. So this is the end of my sessions. If you, again, we are running an informal BOF or a small discussion session after lunch right outside the room. So if you have any questions or anything interesting to discuss or share the stories, we can meet after lunch at 2 o'clock, right? All right, so with that, we have reached the end of AOSP Devroom. Thank you very much for attending this Devroom. A big round of thank you to everyone who is present in the room, to our volunteers, Sahaj, Sumit, our reviewers, Khasim Syed, Vishal and Sumit, our IndiaFOSS organizers, Shri for all the help and all the botherings which we have done at the last minute. Thank you very much, and we'll see you again hopefully next year or in the informal session which we will do after the lunch.
This Devroom has been great. They're even doing the live streaming for us. Can't ask for anything better. Great spirit of community. Thank you guys.
Thank you very much.